Okay, welcome to AI Paper Podcasts. Today we're diving into a paper that really flips the script on how we often think about AI reasoning.
Yeah, absolutely.
You know how we often see large language models generating these intermediate steps, chain of thought, people call it? And the assumption is, well, the model's thinking step by step.
Right. It looks like reasoning.
Exactly. But the core puzzle this paper gets into is, does the actual meaning of those steps even matter?
And the answer they found is pretty surprising. Actually, quite counterintuitive.
Totally. They found that training models on intermediate steps that have like zero relation to the actual problem can work just as well.
Or sometimes even better than training on perfectly correct steps.
Yeah.
Especially for generalization, getting it to work on new kinds of problems.
Which really challenges that whole idea that the AI is doing human-like reasoning in those traces, doesn't it?
It certainly complicates the picture. Big time.
Okay, so that's the quick version. Let's really get into the details now.
Sounds good.
We're looking at the paper Beyond Semantics, the Unreasonable Effectiveness of Reasonless Intermediate Tokens. It's from researchers at Arizona State University.
A really interesting title, too. Reasonless Intermediate Tokens.
Yeah, it sets the stage. So our mission here is basically to unpack what they found and maybe, question some of our own assumptions about what's going on inside these models when they generate those steps.
It's easy to see why the common perception exists, though. You prompt a model, it spits out these steps.
Like step 1, analyze the question. Step 2, identify key entities. It looks like a logical process.
Exactly. And we hear about things like DeepSeek's R1, or people talking about models having these aha moments based on the traces. It reinforces that idea of internal thought.
But this paper asks, okay, how much does the semantic content, the actual meaning of those specific words or tokens in the trace, really contribute to the model getting the right answer in the end?
And they didn't just, philosophize about it. They set up some really clever, controlled experiments to test it directly.
Which is important because trying to verify the thinking process in, say, GPT-4 is, well, it's incredibly hard, right?
Oh, absolutely.
Yeah.
These models are massive, trained on just incomprehensible amounts of data, and the output is natural language, which is inherently ambiguous. How do you prove a natural language trace is logically sound? It's tough.
So their approach was smart. They used what they call a model organism.
Yeah, like in biology. Study something simpler to understand a fundamental principle.
Exactly. So instead of a giant LLM, they used smaller models, trained completely from scratch.
And critically, trained on a very specific formal task. Maze pathfinding.
Right, a classic computer science problem. You got a grid, walls, a start point, and end point. Find the path.
The plan is just the sequence of moves up, down, left, right. And it's correct if it gets you from start to goal without hitting walls.
Right.
Simple, well-defined, unambiguous.
Okay, so they have a clear task.
Yeah.
But they needed the equivalent of that chain of thought, the intermediate steps. How did they get that?
They use the A search algorithm. It's a standard, very effective algorithm for pathfinding.
Okay, I know A. It explores paths based on cost so far, plus estimated cost remaining.
Precisely, and they modified A so that as it runs, it outputs a detailed log of its operations, a linearized execution trace.
So not just the final path, but how A found it.
Exactly. It logs things like create when it considers a new square, puts it on the open list or priority queue, along with its coordinates and costs.
Costs like distance traveled and estimated distance to go.
Yep, the G value, cost from start, and the half value, heuristic estimate to goal.
Yeah.
And it logs close when it definitively selects a square from the open list to expand from.
So this trace is like a very formal, structured chain of thought specifically for this maze task.
That's the perfect way to put it. Structured, formal, not ambiguous natural language.
And the structure is key because it let them build something really important, right? The validator.
Oh, absolutely crucial. They built a formal A trace validator because the trace follows these strict create-close rules based on the A algorithm.
They could programmatically check if a trace generated by their model actually followed those rules step by step.
Exactly. It wasn't about interpreting meaning. It was about checking rules. Does this close action reference a node that was actually created and put on the open list? Did it try to move to an invalid neighbor, like through a wall?
Did it pick the node with the lowest total estimated cost, the F value like A is supposed to?
Right. All those specific A logic checks so that they could get a hard, objective measure of whether a generated trace was valid according to the algorithm's logic. A huge advantage over trying to judge natural language reasoning.
Okay, makes sense. And the model they used?
It was a transformer, but a relatively small one. a modified Quinn 2.5, 0.5 billion parameter variant.
And trained from scratch just on this maze data.
Yes, which is important.
Yeah.
No baggage or confounding knowledge from massive web free training, just learning the maze task and how to use or misuse these traces.
Got it. And the data itself, what kind of mazes?
They train mostly on mazes generated by Wilson's algorithm. These tend to be sort of uniform and tree-like, typically without any loops in the paths.
Okay, so that's the training distribution. What about testing? How do they check generalization?
That's where it gets interesting.
Yeah.
They tested on several types. More Wilson mazes, sure. Also Kruskal mazes, another algorithm that makes loopless mazes. DFS mazes, also loopless but often have long corridors.
So far, all pretty similar structurally. No loops.
Right. But then they tested on two crucial out-of-distribution OD types. Drunkard's walk mazes and search former style mazes.
And the key difference there is?
They can have loops. The paths can circle back on themselves. This is structurally quite different from the training data. So testing on these is a really strong test of whether the model has learned something generalizable or just memorized patterns from the training mazes.
Okay, setup makes sense. Controlled task, formal traces, validator, specific model, careful data sets for training and OD testing. So what did they find initially?
Well, first, they did the baseline check. Train a model just on the final solution paths, the sequence of moves, then train another model on the problem, plus the correct A trace leading to the solution.
And as expected from other chain of thought work.
As expected, providing the correct A trace, traces during training did help. The models trained with traces were better at producing correct final plans compared to the models trained only on the final plans.
Okay, so traces help. That confirms the general idea. But then they looked closer.
Yeah, this is where the first surprise comes in. They looked at the correlation between whether the model produced a valid trace, according to their validator, and whether it produced a valid plan, the correct final sequence of moves.
You'd think they'd be tightly linked, right? Get the steps right, get the answer right.
That's the intuition. But they found only a loose correlation.
Loose how?
If you look at their confusion matrices in the paper, figure 3, it's really clear. There were cases where the model generated a trace that the validator said was perfectly valid, followed all the A rules.
But the final plan was wrong.
Exactly. And maybe even more surprisingly, there were cases where the model produced a trace that was completely invalid. Like, it violated A rules, made nonsensical steps according to the validator.
And yet, the final plan was correct.
Correct. It somehow stumbled into the right answer despite producing a formally incorrect reasoning trace.
Wow. Okay, so that really directly challenges the idea that getting the intermediate trace right is strictly necessary or even a reliable path to getting the final answer right.
Precisely. It suggests the link between the trace's algorithmic correctness and the final output correctness is weaker than you might assume.
So if a perfect trace isn't essential, it leads straight to their big question. How much does the meaning or relevance of the trace content actually matter at all?
Exactly, which set up their core experiment, the really provocative one, using the swap dataset.
Okay, explain the swap dataset. This sounds wild.
It is pretty clever. They took the exact same maze problem, same grid, same start, same goal, same walls. But during training, they paired each maze problem with an A trace that was generated for a completely different, totally unrelated maze problem.
Wait, so for maze A, the model sees maze A's layout, start, and goal.
But the intermediate steps it's shown during training are the A trace for solving some other maze B. Exactly that. The trace looks like an A trace. It has the create, close coordinates, costs format. Syntactically, it's similar.
But semantically, it's complete nonsense for maze A. It's describing steps on a totally different map.
Utterly irrelevant. Useless as actual guidance for solving maze A.
Okay, that's a bold manipulation. So they compared training models on just the solution, the correct A traces, and these swapped irrelevant traces.
Yep, and the results, especially looking at table 1 in the paper for plan validity, they're really something.
Lay it on us.
Okay, first, solution only versus correct traces again. Correct traces helped, as expected.
Standard COTI benefit. Got it.
But now, compare correct A traces versus the swapped A traces. On the in-distribution data, the mazes, similar to training, Wilson, Kruskal, the swapped model performed, well, basically the same, maybe even a tiny bit better than the model trained on correct traces.
Just as good with nonsense traces as with correct ones? That's already surprising.
But hold on. The really significant part is the OD performance. the generalization to those tricky mazes with loops like Drunkard's Walk and DFS.
What happened there?
The model trained on the swapped, irrelevant traces showed a massive performance gain compared to the one trained on correct traces.
A gain? How much?
Okay, look at the Drunkard dataset results. The model trained with correct traces got about 2.5% planned validity. Not great generalization. The model trained with swapped traces, 26% validity.
10 times better by training on irrelevant traces.
Yeah, and on DFS mazes, it was similar. Swapped got around 42% correct plans, while correct traces got about 31%, consistent OD improvement from irrelevant traces.
That's kind of nuts. But what about the traces the swapped model produced? Did it learn to make correct A traces somehow?
Crucial point. Look at the trace validity column for the swapped model in the results table. It's 0%, consistently 0.
So it learned to produce traces that looked like A traces syntactically,
but were just as semantically meaningless for the actual problem it was solving as the swapped traces it was trained on.
Yet it found the right plans more often, especially ode.
Exactly. It learned to generate garbage traces, but that process somehow helped it generate correct final answers and generalize better.
Okay, so the paper's conclusion from this seems unavoidable then.
Right. The semantic correctness, the actual meaning or relevance of the intermediate trace to the problem at hand, is not necessary for the performance boost you get from these intermediate steps.
And, in fact, training on semantically irrelevant but structurally similar traces might even be better for generalization.
That's what their results strongly suggest. The relevance might even hinder generalization in some cases, compared to these reasonless tokens.
Mind blown. Okay, so if these intermediate tokens aren't necessarily working because of their semantic meaning as reasoning steps, what are they doing? How did the researchers explain this?
Their hypothesis is that these tokens might be functioning as a kind of learned prompt augmentation.
Prompt augmentation, like modifying the input.
Sort of. Think about how a transformer works. It predicts the next token based on all the previous tokens, by forcing the model to generate this sequence of intermediate tokens before it generates the final answer.
You're changing the context, the sequence of tokens it sees right before it has to produce the final plan.
Exactly. Generating these intermediate tokens, even if they're semantically meaningless, changes the model's internal state. It changes the input context for predicting the final tokens of the plan.
So it's like the model learns, okay, if I output this kind of structured gibberish first, I'm statistically more likely to output the correct plan afterwards.
That seems to be the idea. It's an automatically learned modification to the effective prompt or context discovered through training because it correlates with better final answers.
And this augmentation doesn't need to make sense to a human. It doesn't need to follow logical steps.
Apparently not. It just needs to be a sequence of tokens that, for whatever reason due to the training dynamics and model architecture, nudges the model's output distribution towards the correct final plan.
They mention a connection to adversarial prompting.
Yeah, they draw a parallel. We know from adversarial examples research that sometimes tiny, seemingly meaningless changes or additions to a prompt can drastically change a model's output.
Right, adding weird characters or phrases can make it bypass safety filters or give wrong answers.
So this supports the general idea that token sequences can have a significant impact on model behavior without necessarily having a direct, human interpretable semantic link to the task itself. It could be more about manipulating the model's internal processing path.
Okay, so the big takeaway here for us researchers and engineers working with these models, what is it?
I think the main thing is be really careful about assuming that output that looks like reasoning actually is reasoning in the way we understand it.
Just because it generates text formatted as step 1, step 2, step 3.
Doesn't mean the model internally executed that logical process, or that the content of those steps holds the semantic weight we'd naturally assign to it. It might just be a useful pattern it learned to emit.
The paper explicitly warns about anthropomorphizing, right? Calling these traces thoughts or getting excited about aha moments based just on the text.
Yeah, they caution that this can be pretty misleading, and potentially it could even hinder progress if we become too fixated on making models mimic human-style reasoning traces perfectly.
When maybe other less intuitive intermediate token sequences are actually more effective for performance or generalization.
Exactly. It shifts the perspective. Maybe the goal shouldn't be force the model to output perfect traces, but rather find whatever intermediate token generation process leads to the best plans, even if the traces look weird.
Focus on the function improving the final output rather than assuming a specific human-like form of internal process based on the intermediate output.
That seems to be the implication for designing and interpreting these systems. It's less about replicating human thought processes verbatim and more about finding effective computational mechanisms, whatever they look like.
Okay, let's try and sum up that core, really surprising finding one last time.
Sure, basically. Training reasoning models with intermediate tokens that are semantically meaningless, completely irrelevant to the problem,
Can be just as effective and sometimes significantly more effective for generalization than training with perfectly correct, meaningful intermediate steps as long as they share a similar structure.
The meaning might not be the point. The structure and its effect on the generation process might be key.
It really leaves you wondering, doesn't it? If these intermediate tokens aren't always thoughts or algorithmic steps in the way we think about them, what are they doing computationally? What kind of internal mechanism is actually being exploited or learned here?
Yeah, what's the actual computation happening? And how should this change how you approach training or fine-tuning or even just interpreting the outputs of models that claim to show their work?
What does it mean for building AI systems that we actually understand and can genuinely trust if the explanations they provide might not reflect their actual operational logic?
Lots to chew on there.
Definitely. Well, thanks for joining us for this dive into really challenging our assumptions about AI reasoning here on AI Paper Podcasts.
Thanks for having me. It was a fascinating paper.